Hello and Assalamualaikum. In this presentation, we will discuss the ARM Cortex A-53 processor. This presentation is prepared by our group members. Our group members consist of Nur Ariana Elisha binti Hamidi, Nur Syahira Hazika binti Nur Rahman, Afika Husna binti Muhammad Khairi, Nur Arifah Alia binti Muhammad Azmi. I will explain to you guys about our chosen processor. We choose ARM. ARM is a family of RISC-based microprocessor and microcontroller designed by ARM Holding located in Cambridge, England. They design and license processor architecture but does not manufacture chip. ARM processor known for small size, high speed, and low power consumption. They are widely used in smartphone, embedded system, and consumer devices. One of the most popular processor is Cortex A-53. It's based on ARMv8 architecture, which support 32-bit and 64-bit processing. It's suitable for mobile and embedded application. ARM offers two types of listenable product. Firstly is processor. Its company can use ARM ready-made processor design, and the second one is processor architecture. They can design their own processor following ARM architecture standard. The Cortex A-53 is designed by ARM Holding and licensed to companies like Apple, Qualcomm, Samsung, and MediaTek, who integrate it into their system-on-chip designs. ARM used the RISC, or known as Reduced Instruction Set Computer architecture that focus on high performance with low power consumption. ARM processors are designed by ARM Limited but not manufactured by them. The Cortex A-53 is optimized for energy-efficient performance, support multi-core configuration, and is commonly used in smartphones, tablets, and embedded systems, and making it ideal for battery-powered devices. ARM Cortex A-53 is a 64-bit, low-power processor designed for devices that require good performance with minimal energy consumption, such as mobile and embedded systems. In terms of CPU organization, the Cortex A-53 consists of four main components, which is the front end, execution engine, memory subsystem, and cache. The front end is responsible for instruction fetching, decoding branch, reduction, and dispatching. Ensure that instructions are efficiently delivered to the execution unit. The execution engine includes the arithmetic logic unit, ALU, and floating point, which perform arithmetic, logical, branch, and SIMD operation. The memory subsystem manages data access through the L1 cache, load or store units and buffers, while the 256 KB L2 cache improves instruction and data access speed. The control unit coordinates all CPU operation, manages the pipeline, resolve hazards, and maintain high performance with low power consumption. It also works together with the branch predictor to improve efficiency and reduce execution delays.
My name is Nur Syahira Hazika binti Nur Rahman, and I represent from part 2.2 until 2.4. This slide explains the register set and what registers do in the CPU. Registers are very small and very fast storage locations inside the processor. First, we have general purpose registers. These are 64-bit registers used for normal operations like calculations, logical operations, calling functions. They can also work as 32-bit registers, which allow the system to support both 32-bit and 64-bit programs. Next are special registers, which control how the program runs instead of storing normal data. The program counter, or PC, holds the address of the next instruction to be executed. The stack pointer, or SP, points to the top of the stack and is used during functions called to store data like local variables. The link register stores the return address when a function is called. Finally, the frame pointer helps organize the stack and is useful for debug. In short, registers help the CPU run programs quickly and correctly. For the next part is 2.3, which is system bus. This slide explains system buses and how different parts of the computer communicate. A bus system is like a highway that connects the CPU, memory, and input or output devices. It carries data, address, and control signal between these components. In this architecture, each CPU core has its own L1 cache, and all cores share a common L2 cache. A control unit keeps the caches consistent so all cores see the same data. The system also connects to other components like memory, GPU, and peripherals such as UART, GPIO, and timers. High-speed components use faster buses, while slower devices connect through a bridge. There are three main types of process. First, the data bus that transfer actual data. Second, the address bus decides where data is read from or written to. Third, the control bus sends signals like read, write, and timing. Overall, system buses allow all parts of the computer to work together efficiently. To the next part, which is 2.4 cache memory organization. This slide explains how cache memory is organized in the ARM Cortex A-53. Cache memory is small, fast memory that sits between the CPU and main memory. Its purpose is to reduce delay by keeping frequently used data close to the processor. The Cortex A53 uses a two-level cache system, which is L1 and L2. Level 1 is private to each core, and each core has two parts. First, an instruction cache for instructions, and two, a data cache for data. Both are small but very fast, which helps the CPU run instructions quickly. Level 2 cache shared by all cores. It is larger and slightly slower than L1, but still much faster than main memory. L2 stores data and instructions that are not found in L1. Overall, these cache organizations improve performance, reduce memory access time, and ensures that all cores see the same data in a multi-core system.
My name is Afika Usna binti Muhammad Hairi and I would like to present 2.5 until 3.4. First is the main memory and input-output component, which is in 2.5 in the ARM Cortex A53 system. Since this processor is widely used in mobile and embedded device, its memory hierarchy is carefully designed to reduce latency and improve the performance. First is L1 cache. It's small but very fast memory located in each core. It stores frequently used data and instruction, helping the processor respond quickly. And it comes to the L2 cache, which is the larger and shared across the multiple core. Beyond the cache is the main memory or DRAM. It offers much more capacity but takes longer to access. It's managed by a memory controller and is used for storing active data and program. At the bottom of the hierarchy is the secondary storage, like SSD or HDD. These provide huge storage space, but are most slower. They are used for long-term data storage and access through input-output subsystem. Next, we go to the input-output controller. These include controllers that manage communication between the CPU and device like sensors, display, and network modules. They translate CPU instruction into signals that device understand. Now we go to 3.1, which is the overview of the instruction cycle in the ARM Cortex A53 processor. This cycle is the core process that allows the CPU to execute instruction efficiently. The instruction cycle is made up of the three main stages, which is a fetch, decode, and execute. These stages form a continuous loop that the processor follows to handle every instruction. The ARM Cortex A53 uses an in-order pipeline, meaning that instructions are processed in order they arrive. This design helps to keep the processor simple and power off the efficiency. By using pipelining, the Cortex A53 can work on multiple instructions at once, which is in fetching, decoding, and executing. All is in parallel. This improves performance while keeping power usage low, which is ideal for mobile and embedded system. Each instruction goes through these stages to ensure that it's handled correctly and efficiently. We go to the 3.2 until 3.4, which is the three core phase of the instruction cycle in the ARM Cortex A53. For the first phase is the fetch phase. Here the processor retrieves the next instruction from memory using the program counter, which is the PC. This instruction is then stored in the instruction register, which is IR. To speed things up, the processor uses an instruction cache, which holds the frequently accesses of the instruction. Once the instruction is fetched, the PC is updated to point the next one. Next is the decode phase, which is in 3.3. In these stages, the CPU analyzes the instruction to figure out the operation it needs to perform. Then it identifies the operation type, the required operand, and the destination of the register. The instruction decoder interprets the opcode and generates the control signal. The CPU also reads the data from the registers to prepare for execution. Last is 3.4, which is the execute phase. This is where the processor performs the actual operation. If it's an arithmetic or logic instruction, the ALU handles the computation. If it's a load or store instruction, the CPU calculates the memory address and access data through the data cache. For branch of instruction, the program counter may be updated to change the flow of execution. So, these are three phases form the core of how the ARM Cortex A53 processes instruction efficiently and accurately.
This slide illustrates how data is processed inside the ARM Cortex A53 processor through the instruction cycle. The process begins with the fetch stage, where the processor retrieves an instruction from memory using the program counter. The instructions is then stored in the instruction register, and the program counter is updated to point to the next instructions. Next is the decode stage, where the control unit analyzes the instructions to determine the type of operations to be performed. During this stage, the required registers are identified and the necessary data is read from the register file. To conclude this presentation, the ARM Cortex A-53 is a 64-bit, low-power processor core designed for energy-efficient computing. It uses an in-order execution pipeline and a relatively simple microarchitecture which helps reduce power consumption, minimize heat generation, and extend battery life. While the Cortex A53 does not deliver the same peak performance as higher performance cores such as the Cortex A57, it provides sufficient performance for everyday tasks and balanced workloads. The Cortex A53 is particularly effective in systems that prioritize efficiency, reliability, and low cost over maximum performance. This is why it is commonly used in mobile devices, embedded systems, and lot applications. Overall, the ARM Cortex A53 demonstrates how efficient processor architecture design can meet modern computing demands while maintaining low power consumptions and high reliability.